Hello everyone, and thank you for joining. Today's webinar is PurgeAndTrap201, Optimizing Parameters for EPA Methodologies, and will be given by Jacob Repholz. We will be taking questions and answers at the very end, so please feel free to submit your questions using the question function throughout the webinar, and Jake will answer them at the end. So Jake, I'm turning it over to you.
Excellent, thank you. Welcome, good morning everyone. Thanks for joining in with us. Hope everyone's safe and warm wherever you are. I know we got quite a bit of snow here in Cincinnati. But today we're going to be talking about purge and trap parameters and optimizing those parameters for EPA methodologies. And can I?
You've got to submit 5
there we go. Excellent. Having a little trouble advancing my slides. So today we're going to talk about several topics. We're going to start with carryover, discuss sources of carryover and our control methodologies for that carryover. Then we'll move into water control, why water is bad for our analysis and how to control it. We'll look at condensate trap considerations, dry purge considerations, desorb and bake. And then finally we'll end with some special considerations for soil purge, specifically addressing carryover issues, in-vial purge considerations, mixing considerations, and methanol extractions. And then at the end, we'll take questions. Okay, so starting, what is carryover? Carryover is any time we are seeing some of our target compounds in moving from one sample to the next. So for instance, if we were to run a high concentration standard and then the blank immediately following had some target compounds in it, that would be carryover. Why is carryover bad? Well, it causes a loss of productivity and a loss of sensitivity. So when we have carryover, we have to spend more time cleaning, so maybe running rinse cycles in our purge and trap system. That leads to fewer samples being analyzed per hour, and if we're having trouble finding the source of that carryover or contamination, we spend a lot of time troubleshooting and trying to find that source, and that pulls us away from much more important things that we could be spending our time on. So, first place to start with is how much carryover is too much. Well, if we go to our EPA methods, we find that there are no specific requirements for carryover. There are really no suggestions for acceptable levels of carryover, and there are very few suggestions for what constitutes adequate system cleaning. So, how much carryover is acceptable? Well, we like to suggest that blank concentrations run after high concentration standards should be at least below MeOH or a method detection limit. So what we want to try to do is select method parameters that will both minimize our carryover but also minimize our sample runtime. If we were to do 5 or 6 rinse cycles and bake out our trap for 4 hours between samples, we could ensure that we had no carryover. But obviously we would spend way more time cleaning than necessary, and that would greatly reduce the number of samples we could run. On the flip side, we could do no cleanup cycles whatsoever, so no rinses and no bake out. We could run many, many more samples, but we would have significant carryover issues. And so what we want to try to do is find that nice balance where we're as clean as we need to be, but we can analyze as many samples as possible. So how do we do that? Well, the parameters we're talking about here in our software for the Atomx and Aquatech 100 and Stratum would be found in the Bake tab of the method. And so we're talking about our bake rinses. So how many are we going to use? What volume of rinse water are we going to use? In the case of the Atomx, we have a methanol rinse available. So are we going to rinse with methanol? If so, how many rinses and what volume? And then finally, for the gas side of things, the analytical trap, we're talking about bake times, bake flows, and bake temperatures. So we want to make sure that we're baking out at least warm enough to drive everything off of the trap, using enough flow of gas through the trap during bake to ensure that we remove all of the target compounds that were left over, and then making sure that we let this process run long enough to give us adequate cleanup. Okay, so what are our sources of carryover? Well, we can break our sources down into 2 main categories. We have our liquid handling pathway, which is typically the auto sampler, so the preparation portion, as well as the sparger of the concentrator. So all of our sample glassware. pressurized sample loops on the Aquatech 100. We would also include the syringe on the Atomx, as well as the glass sparger. On the gas handling side of things, we have the analytical trap. We have the transfer line to the GC. We have all of the associated plumbing that moves our gases from the sparger to the trap to the transfer line. And then we also have the GC itself, including the inlet and the analytical column in the GC. So how do we go about troubleshooting these issues? First, we want to determine what type of carryover are we seeing. Are we seeing a full list, target list carryover, or are we only seeing the later compounds being carried over? And this will start to give us an idea of what types of issues we might be facing. When we go to look and see where our carryover or our contamination is occurring, we want to start by separating our systems and working through them one at a time. So the first and easiest one to eliminate would be the GC. So immediately after running a high concentration standard, we could run the GC only with no desorb and see if we see our target compounds come through then. If we do, then we know we have an issue with contamination in either our inlet or our column in the GC. If we don't see contamination there, next we would run a desorb only on our concentrator, run the GC, and see what we get. If we see our compounds being carried over during desorb only, then we know that we're not getting adequate cleanup of our analytical trap, or we have compounds hanging up in our transfer line, or they're hanging up somewhere in the associated gas lines that go from the trap to the transfer line to the GC. If our problem is coming during desorb only, then the things we'd want to check would be the temperature of our bake between samples. We'd also want to check the temperature that we desorb at to make sure that we're heating the trap up high enough to release all of the target compounds. And then we want to look at making sure our bake flows and our bake times are long enough to give adequate cleanup. If we do not see our carryover coming during desorb only, then it's likely that our carryover issues are on our water handling side. And so at that point, we would want to check to make sure that we are adequately rinsing so that our water is hot, make sure our heater is working properly, make sure that we're actually transferring the water during the rinse cycle, and then maybe consider adding a methanol rinse if available, or maybe increasing the number of rinses, both water and methanol, that we use. Okay, so how does this break out more specifically? When we're talking about a full target list carryover, if we're seeing it in the GC, we could have an issue with our electronic pressure control. So we're not getting a consistent flow of gas through our GC. And so this can cause some of the desorbed gas to be hung up in the inlet or to get hung up in the trap, or the column, excuse me, not be pushed all the way through to the detector, and then it gets carried in with the next sample. If the issue is not coming on the GC side, on the purge and trap side, we could have leaking valves allowing purge gas or desorb gas to access portions of the sample pathway that it's not supposed to. Especially during desorb preheat, when we seal the trap and we heat it up, we generate pressure. And if those valves are leaking, we can allow some of that desorb gas to flow back into the system towards the glass spargeware. And then on the next sample, that desorb gas would be carried back into the analytical trap again, giving us a carryover of all of our target compounds. We could also have a faulty trap heater, so we're not heating the trap as warmly as we think we are, so we're not driving all of our compounds off. Maybe we're not heating it at all, so our bake-out cycle is not actually heating the trap up, it's not actually baking anything off. If our issue is coming from our liquid side of things, we could have the sample not draining properly out of the glassware after purge. And this could be due to a clogged drain, or it could just be due, especially with the Atomic, or with the AT100, if we don't set that drain time long enough. Since that's a pressurized system, we have to push that water out of the sparger for a set amount of time, and if we don't have that set long enough, we can leave some of that water behind. We could also have dirty glassware that's causing compounds to adsorb to the glassware and remain from one sample to the next. In addition, on our auto sampler side, on our preparation side, if we have the option to do an in-vial soil purge, we could run a soil purge and then check that against our water purge. So if we don't have carryover in in-vial purge mode, but we do have carryover in the sparger purge mode, then we know that it's a water handling issue. So again, maybe not draining that sparger properly. we may not be rinsing properly. There could be an issue where either the water is not hot enough or it's not being transferred to the sparger during the bake rinse. We could also have an issue with our internal standard injectors, especially if you're using one of your internal standard vessels to generate your continuing calibration checks. So you have your target list spike in that vessel. If that injector is leaking, we could be putting small doses of our compounds into every single sample that comes through. That's going to give us a full target list carryover. And then finally, we may not be transferring our full aliquot of sample to the sparger. Again, especially with the AT100, if we don't set that pressurized time long enough, we may not completely empty that sample loop, and so whatever portion of water is left behind in the loop is going to be diluted into the next sample, and that's going to give us carryover. So here's a chromatogram showing a full target list carryover. So we see even down here in the early stages, we have our gases, including vinyl chloride right here. Quite a significant amount of carryover here. Ran a 200 ppb standard, followed immediately by a blank with no bake rinse. So that's how I was able to generate this. And so we can see that if we don't rinse our glassware, even if we drain it completely, if we skip that rinsing cycle, we get quite a bit of carryover, all the way down to our late eluters. Everything comes through. If we're only looking at our late eluters, so our heavier compounds, then we have a different set of issues that we're looking at. On the GC side, our inlet may be too cold, so these compounds may be adsorbing to the inlet, not being carried onto the column, not carried into the detector. On the purge and trap side, we may not be using long enough of a bake. Our bake may not be hot enough. This could be due to, again, a bad trap heater. We could have a bad trap. We may just be hanging on to things that we should be releasing because our adsorbents are going bad. We could have cold spots within the system. So if any part of that tubing and that transfer line that moves our gases from the trap to the GC is cold, it's going to cause especially the heavier compounds to be held up there. One spot that tends to always cause this issue is our actual connection between the transfer line of the purge and trap concentrator and the GC inlet itself. That's a spot, so the transfer line is heated, the inlet is heated, but that union, that connection there often is not directly heated, and so it relies on passive heating from those other two sources, and if it's not insulated well or if it gets cooled too much, we can lose our late eluters getting hung up there. On the auto sampler side, again, if we have the option to do an in-vial purge, we can run that and compare it to our water purge. Or if we're doing in-vial sample purging and we're seeing carryover, we can run a water purge and see if we also see that carryover. That'll help us sort out whether it's in our sparger or our syringe or water handling portions of the auto sampler. We could have a water heater failure, so we're not heating our water enough during our bake-out rinse, so we're not removing those heaviest compounds. We may not be doing enough rinses, so maybe we need to add more water rinses or we need to add a methanol rinse to the sequence. Finally, we may not be rinsing our needle properly, so we may not be getting good sample needle cleanup, or we may not be transferring our bake rinse to the sparger, again, especially in pressurized loop systems. If we don't pressurize long enough to fill that loop completely, and then if we don't transfer long enough to transfer that full aliquot from the loop to the sparger, then we're not going to get adequate rinsing, adequate cleanup. So how do we control our carryover? On the liquid side of things, with the Atomx, we have the Extract-EPA, which is a patent-pending methanol rinse system. And what this does is it rinses the entire liquid pathway. So this includes the syringe, the associated transfer lines, the valves, the internal standard injection manifold, the three-stage needle, and the sparger glassware. We can vary the volume and the number of rinses that we do. So for instance, we're using the 5 ml glassware. We can use 7 mils of methanol to make sure we get adequate rinsing of that glassware. If we're using the 25 ml sparger, we can transfer 27 mils of methanol so that we get an adequate rinse of the 25 ml sparger. We also offer our OptiRinse dual heating chamber water heater, and that ensures that we always have a consistent 90°C water to rinse that entire sample pathway. So we can choose to run the water only, or to utilize methanol and then follow it up with a water rinse. And this is recommended actually if we're going to use a methanol rinse, we should follow it with a water rinse to make sure we remove that methanol so then we don't have methanol carryover from one sample to the next. All right, so here's some carryover control data. We're looking at our last 4 eluters. So hexachlorobutadiene, 1,2,4-trichlorobenzene, naphthalene, and 1,2,3-trichlorobenzene. And we see here that with 1 water rinse, 2 water rinses, and 3 water rinses, we reduce that carryover. I should say here this was a 200 ppb standard, and our y-axis is percent carryover. So, for instance, with hexachlorobutadiene, we see whether we do 1, 2, or 3 water rinses, we still get right around 0.5% carryover. We're not adding additional rinses is not getting us a better carryover rate. And so this shows that adding 2 or 3 water rinses is just wasting time. We're extending the length of our run for no reason. Whereas if we use a methanol rinse, we see that we now get a significant reduction in carryover for hexachlorobutadiene. And we see a similar trend with the trichlorobenzenes as well. Naphthalene is cleaned up pretty well with water. Methanol doesn't improve it quite as much. You can see, again, here's an opportunity for optimization. So we can run 1 methanol, 1 water rinse. Now we've done 2 total bake rinses, and we've gotten much better carryover results than had we done 3 water bake rinses. Then again, we're looking at the same last 4 eluters, so hexachlorobutadiene here, 1,2,4-trichlorobenzene, naphthalene, and 1,2,3-trichlorobenzene. The blue line is using 1 water rinse of our glassware, and then the green line is using the methanol rinse. And so we can see a significant reduction in that carryover rinsing the pathway with methanol. Okay, so what about carryover control on our gas side of things? First and most important thing we can do is eliminate or reduce our cold zones. So that includes making sure that connection between the inlet and the transfer line stays nice and warm. Make sure that our trap stays nice and warm when it needs to be. Making sure that all the associated plumbing between the purge and the desorb stays nice and hot so things don't get held up. To this end, we use a U-shaped trap. That way we reduce the amount of sample pathway, which also reduces the opportunities for things to get hung up and carried over. Inert tubing helps with this. And again, our bake sequence, making sure we optimize our bake options so that we drive off any volatiles that are left in the system between samples so that we start fresh and clean each time. So here's a picture of the stratum, and we see here that we have our heated transfer line. We have our heaters on our analytical traps and our condensate traps so we can bake the system out. We also have our 6-port valve remains heated. The port that goes to the sparger is heated, and all of this tubing is all inert and remains heated within this oven, helping to reduce cold spots and carryover. So what are our conclusions on carryover control? For liquid pathway carryover, we want to make sure that we use adequate rinses of water, including methanol if necessary or when necessary, and making sure that those rinses are working properly. So the water is being transferred over to the sparger, making sure that it's hot. So even just touching your sparger as your water is being carried over, do you feel it warming up? Is that hot water that's coming in there? Also, on the gas side of things, we want to make sure that we reduce or eliminate our cold spots. And then again, make sure we optimize our bake times, our bake flow rates, and our temperatures to ensure cleanliness. But also possibly reducing those times if we have them set too long. So finding that nice sweet spot where we can get adequate cleanup but not extend our runtime so much that we start losing productivity. Now I'd like to move on to water control. If any of you are seeing water peaks like this one, which is reaching out almost to 6 minutes, you know how frustrating that can be. Now obviously this is an extreme example, but it begs the question of why do we not like to see water in our chromatograms? Well, there's a number of reasons why we don't like water in our systems. The water peak will reduce the sensitivity of our early compounds, including our gases that come out with the water. Many of the gases are hard to analyze as it is. When those sensitivities are reduced by water, it becomes even more difficult. Water causes coelutions and will cause shifts in our retention times. So from one sample to the next, things are moving around. It becomes more difficult to analyze our data. Moisture will affect our peak shape, even in compounds that are outside of our water peak. So once that water is introduced into the system, it starts to wreak havoc on all of our compounds. Water also will shorten the column life of your GC column and can cause vacuum issues if you're using a mass spectrometer. So how do we deal with water? What do we do? On the purge and trap side of things, on our concentrator side, we want to look at our condensate trap settings. We possibly have a failure of a heater in our condensate trap. We may not have optimized our dry purge settings. We can also look at our purge temperature issues. So for some methods, especially when we get into 8260, some of the less easily purged compounds, we can heat our samples. But there's a trade-off between heating. The more we heat, the more we can dry volatiles out of solution, but also the more water vapor we create that we have to deal with down the line. Finally, we can look at our desorb times. So shorter desorb times move less total mass from the trap to the GC, and that includes water, so we can reduce water that way. On the GC side of things, we can look at our split ratio. So we may have our split ratio set too low, so we're allowing too much of that water to go on the column. A long water peak could be a sign of a bad column. And on the mass spec, we could be looking at vacuum issues. So maybe we don't have adequate vacuuming, so that water that is making it to the mass spec is causing more problems than it otherwise would. Okay, so let's start by looking at our EPA method requirements. So when it comes to our purge flows, our desorb times, these things, what do we have control over? What can we change within our methods? So what are our areas of opportunity for optimization that are going to allow us to deal with this water? In 524.2, we see that we don't really have a lot of freedom. Our purge temperature has to be atmospheric, which actually plays into our favor here. So we generate less water vapor than if we were heating our sample. We have to use a purge flow of 40 mils per minute. We have to purge for 11 minutes, giving us a total volume of 440 mils. We use 25 mils of water, so we're removing quite a bit of moisture as we purge that water. We have to use a 4-minute desorb time, so we don't really have control there. We can't shorten our desorb to put less water on column. Finally, we have to have a certain amount of gas moving through our GC during desorb. But we actually do get some relief here because we have a little more room to play with our split flow, our split ratio, so we can vent some of that water off. Looking at 524.3, again, another drinking water method. Here we have much more freedom, so we have much more opportunity for optimization. Our sample temperatures can range anywhere from ambient to 60 C, recommended maximum being 40. With purge flow, we have more room. We can go anywhere from 20 to 200 mils per minute. Same with our total volume, so we can adjust our purge time or our purge flow rate. We can mess around with our desorb time. We can go as little as 30 seconds or as long as 4 minutes if we want. So if we're having water issues, we could potentially shorten our desorb time. So room for movement here. So by comparison, 524.3 allows us to use 5 mils instead of 25 mils of sample. So when we purge that, we generate less moisture that we have to deal with later. We were not allowed to heat in 524.2. We can now heat our sample in 524.3, which may help us boost our analytical sensitivity for some of our more difficult to remove organics, or volatiles, excuse me. We can optimize our variables in 524.3, which is a huge help with dealing with water while also increasing the sensitivity of our analysis. No changes are allowed that exceed those maximum settings, though, or the min. So we have to stay within that window. We're just finally allowed to move around. Finally, we can utilize sim mode for some of our poorer responders in 524.3, but for our THMs, we still have to stick with a full scan mode. and that's usually not a problem. Moving on to the 5030s. And these are the purge requirements for 8260, 8221, and 8215. We have some freedom for our purge gas, so we can use either nitrogen or helium. Flow rates are set for purge. The purge times are set. Temperatures must be ambient. For B, we can use up to 85 degrees C in 8015 under 5030C. Our desorb temperatures are set, and then our backflush flow rates are set. Our desorb times are set. So not as much that we can play with here, but we still have some control over a few of our parameters. And then finally with 5035, this is the in-vial soil purge. We have a little more freedom, both in purge temperature, our purge flow rate, so we can choose our total volume of purge gas, and our desorb time. So again, some things we can play with to help handle water in our systems. So how do we put all this together? Well, when it comes to water control, we have four main areas that we can handle water and that we can work to minimize it. We have our condensate trap, and we'll get into some of the theory behind condensate traps, discuss a little bit about packed hydrophilic condensate traps. We also remove water during our dry purge stage. So again, a little bit about that, how that works, how to optimize that. We can deal with water both in our desorb preheat, and this ties back to our condensate trap, and then also during desorb, primarily length of desorb, so we'll discuss that. And then finally, our bake cleanup at the end of our sample, making sure that we adequately remove any leftover water so that we don't accumulate water in our system and cause water peak issues down the road. Okay, so condensate traps. Condensate trap is an intentionally cold zone within our heated gas path line. And what this does is it allows that water vapor to condense and collect as a moisture, removing it from that gas stream. And ideally, we would like to do this without also retaining our target compounds. So there's two ways to remove this moisture. We can either do it with that open trap that's at a colder temperature, or we could use a packed hydrophilic trap. And we'll get into each of these. So for the open condensate trap, we use a U-shaped trap, so that allows when that water vapor condenses to liquid, it pools at the bottom, and then it's baked out after the completion of desorb. So we then heat that trap up, just as we do with the analytical trap, to remove all of that moisture. However, the temperature that we set our condensate trap at can have an effect on peak shape. So when we create this cold zone where our gas is going through, that can cause to either slow down or speed up our target compounds and broaden our peak shapes. So there's some trade-offs here. We get moisture removal, but we affect our peak shape. And so again, we want to find that temperature that allows adequate removal of moisture without affecting our analysis too greatly. So our hot purge gas, as I mentioned, goes into our cool tube. Water vapor condenses. But we remove most of our water during desorb preheat. So that's the moment where we finish purging. We close off our analytical trap and our condensate trap, and now it's sealed from the rest of the system. As we continue to heat our analytical trap to just below our desorb temperature, our gases within the trap are expanding, and they have nowhere to expand to other than the condensate trap. And so as they expand into there, the moisture cools against that cooler tube and condenses out. And then during desorb, again, we're still flowing through that condensate trap, so we're still getting some water removal. However, we have very little moisture at the bottom, so the gases are flowing over top. They're not bubbling through that moisture, and so they're not recontributing a significant amount of moisture back to the sample. And so we see here that during purge mode, we're running our gas through our condensate trap here first, then through our analytical trap. So ideally, we're getting some moisture removal before we ever go on the trap at all, and that's going to help reduce the amount of moisture we put onto the trap. And then later, we'll see that we're also still flowing through that condensate trap. During our desorb preheat mode, we're open to it, and then during desorb, we're going through that condensate trap. So we're always getting opportunities to remove water with our condensate trap. Okay, so this brings us to packed hydrophilic condensate traps. And these use a material that has a high affinity for water and ideally a low affinity for our target compound. So you can think of it as like an anti-trap as compared to our analytical trap, which we choose the adsorbents so that they have a high affinity for our target compounds and a low affinity for water. Packed hydrophilic columns give excellent moisture retention, so they do contribute greatly to the reduction of our water peak. However, they can show an affinity for alcohols and highly polar compounds. Therefore, they're not good for oxygenates analysis, for instance. So here's some data. What we're seeing here is the temperature of our condensate trap during purge and desorb. And as I mentioned, the temperature of that trap can start to have an effect on our peak shape. So we see here, especially with our TBA, at 20 C, we have a nice broad peak. And as we increase that temperature to 40 and then 150, that peak tightens up. So we get narrower peaks, sharper peaks. But obviously at 150 C, we're not removing water with that condensate trap. So at this point, the trap is just as hot as the rest of the system and is not contributing to a moisture removal, simply to giving good chromatographic results. So there's a trade-off here. Okay, the final way that we can also control water through our dry purge, and this is a flow of clean, dry gas through our analytical trap just prior to desorb to remove moisture. So the larger volume of dry purge gas we put through, so the higher flow rate, or the longer that we dry purge for, or by increasing both, we're going to remove more moisture. The trade-off here is that if we go too long in our dry purge, or if we use too much gas during dry purge, we can start to remove some of our lighter target compounds, which we obviously do not want to do. So we see here during dry purge, we're taking our gas through the condensate trap first, then through our analytical trap, and then out to vent. And so we're pushing that moisture off of the analytical trap. And again, room for optimization here, making sure that we get adequate moisture removal or contribute to adequate moisture removal without using so much flow that we start to remove our gases or some of our lighter, more volatile compounds. And then to that end, we see here that when we use a dry purge of 200 mils for 2 minutes, so hit with a lot of flow, but for a short amount of time, we get nice sharp peaks and we get good recoveries of some compounds, such as our TBA, our ETBE, and our TAME. However, with a longer dry purge and a lower flow rate, more time, more exposure to that gas flow is going to start to strip off certain compounds, such as, again, our TBA, our ETBE, and our TAME. So it's not only just the total amount of gas you put through, but also the amount of time that you're allowing gas, your lighter compounds, to be exposed to that gas. They can potentially be stripped off. So finally, that brings us to desorb. And desorb is our last and often one of our greatest tools for controlling water here, in that we can adjust our desorb time to help adjust the amount of material that we put onto the GC. So a longer desorb means we're going to remove more of our compounds from the analytical trap to the GC, including water that may be in there, and it's going to give us a longer water peak. If we shorten that desorb time, then we move less of that material to the GC, so we have a shorter water peak. So this gives us an opportunity for optimization here, both in the length of our desorb, but also the temperatures of our desorb. So a nice rapid and high increase of temperature during desorb preheat is going to cause that expansion that I discussed into the condensate trap, allowing for removal of moisture in the condensate trap. And in the final temperature of desorb is going to help make sure that that moisture stays out of our gas flow and that we transfer everything we want to the GC. So we see here in our desorb preheat, we don't have flow coming in here, and we don't have flow coming out of here. And we heat all of this And so our gases are going to expand out of our analytical trap into our condensate trap, which is going to be cooler than the analytical trap at this stage. And that's what's going to cause our condensation and our removal of moisture. Then during desorb, we open up our system, so our GC carrier gas comes in, flows backwards through the trap as compared to during purge, then through the condensate trap for one last opportunity to remove some moisture before going on to our GC. Okay, so now let's get some examples of how desorb time can actually affect our water peak. So here we have a 4-minute desorb, and we see that our water peak goes out to right around 4 minutes as compared to a 2-minute desorb where we've shortened our water peak down to about 3 minutes and 30 seconds. More importantly, now our first standard here, our first internal standard is now out of our water peak, and so we're going to get more consistent area counts on that standard, which is going to give us more consistent analytical results moving through our samples. And then if we compare those, we see quite a significant change in the length of our water peak here. So our 2-minute is ending out here 3.4 minutes, with our 4-minute going all the way out to 4.8. And again, so that's quite a few more compounds now that are not in our water peak and are going to be more consistent from one sample to the next. Okay, finally, we have our bake. And what our bake is going to do is remove all of this moisture that we've trapped and we've removed from our gas flow out of our system so that we can continue to remove water from each sample that comes next. And just like we mentioned earlier, our bake out is also going to help with carryover prevention. The temperature we use for bake is going to be dependent on our trap, so we're going to want to make sure that we don't overheat our packing material, causing breakdown of our adsorbents. And then our areas for optimization here would be our length of our bake and the temperature of bake. So making sure that we get hot enough and we flow, our bake gas flows through the trap long enough to remove all of the moisture from the condensate trap and the analytical trap without going for too long. Because again, we could bake for 5 hours, but we're just wasting time at that point. Conversely, we could bake for 30 seconds, but that might not be enough. So just finding that area where we get adequate cleanup without going for too long. Okay, controlling water on the GC side of things, we can adjust our split ratio. So a higher split ratio means more of that desorbing gas coming to the inlet is going to be blown off to vent. Less of it's going to go onto the column. So a higher split ratio means less water is going to go into the inlet onto the column. But it also means that less of our target compounds are going to go into the inlet as well. So we're going to be blowing some portion of those off also. So if we have our split ratio set too high, obviously we're going to start to lose analytical sensitivity. So we need to find that zone that gives us the best of both worlds. And so here we can see examples of that. The blue lines down here are an 80-to-1 split. The orangish that we have up here is a 40-to-1 split, which obviously is putting much more compound onto column. More of that makes it into the mass spec in this case. And then we see with a 100-to-1 split, we have our smallest peaks down here. Now, if these peaks are plenty sharp enough, and if we're getting good enough recovery, so enough area counts to adequately calibrate, and we're getting the reduction in water that we want to see, a 100-to-1 split may be fine. If we're not getting enough target compound into our detector, and we're not getting enough area counts for calibration, then obviously we have to go with a lower split ratio. Okay, so conclusions on our water control. Our first line of defense, and arguably our best line of defense, is our condensate trap. It removes water during nearly every stage of our concentrating, from during purge and trapping all the way through desorb. Hydrophilic packing will absorb water, but it also absorbs some of our polar compounds, such as oxygenates. We also have some room to make changes to our dry purge in many of our EPA methods that we discussed. And so the dry purge removes water from that analytical trap. Any that wasn't removed in the condensate trap and made it to the analytical trap, we can now drive off with a dry gas flow. Again, more flow means more moisture removed, but it can also cause a loss of our lighter compounds. So we don't want to put too much purge gas through there, and we don't want to do it for too long. During desorb, like we mentioned, the length of our desorb is going to affect the amount of water we put onto the column. So longer desorbs means more water, shorter desorbs means less water, but also less target mass making it to our inlet. And then finally we have our GC split ratio. So by increasing our split ratio, we vent more of the water off, and we don't put it onto the column, but we also vent off more of our target compound mass. So we get lower sensitivity in our detectors. Okay, so now let's move on to soil purge. So what are some of the, we're going to discuss some of the special considerations that go with in-vial soil purging and methanol extraction. Some of the general considerations we want to keep in mind is sample preparation. So how do we collect our sample? How do we preserve our sample in the field? And that's going to depend on the methods that we're following. We need to look at mixing considerations. 50-30 and 50-35 require that the samples be mixed. We're going to look at sample heating, which is allowed under certain conditions. And then we're going to give special attention to any carryover issues that we may face with in-vial purge and how to prevent those carryovers. Okay, so let's look at our EPA method requirements. First, we have 50-35. Highly recommended that we use 5 grams of soil. However, if you do your initial demonstration of capability and you prove that you can get excellent sensitivity with less soil, or if you show that you need more soil to get good sensitivity in samples, we can do that. Our main constraint here becomes our ability to effectively weigh out the sample. So if we get to amounts that are too small, are we really getting a representative sample if we're taking what ends up being a couple grains of sand or a couple clumps of clay? Is that really a representative sample of the whole soil itself? And our other issue is how full we end up filling our vial. So making sure that our needle doesn't go below the surface of our soil and become clogged. Purge water volume, so the amount of water we're adding to that soil sample is set at 5 mils. Again, we can change that if we can prove either it's necessary to get the type of sensitivity we need or that we can still get good sensitivity after reducing it. The big concern here is making sure that we add enough moisture that our needle can go down into that water column. It needs to be submerged so that we're actually purging. Standards, so your internal standard and your surrogate standard should be added by the auto sampler. And then finally, there needs to be some type of mechanical mixing of that sample during purge. So in the case of the Atomx, we would be using a stir bar with a magnetic stirrer. So for soil purge, if you're doing a hand extraction on low-level soils, so low-level soils are anything below 200 micrograms per kilogram. What one would typically do is add water to the sample, shake it, remove that water, add it to the Purge and Trap sparger, purge it, continue on as if it was a water sample. However, with the Atomx, we can do our purging in vial. So again, for low-level soils, anything less than 200 micrograms per kilogram, we collect our soil sample, our 5 grams of soil, into a 40 ml VOA vial, add the stir bar at the time of collection, cap it, and now that sample is never opened from that point forward. So we don't have to risk losing any of our volatiles that may have escaped to our headspace by opening it to add water, opening it to add internal standards as surrogates. The Atomx will add the water for us via the reservoir, the DI water reservoir. It adds the internal standards and the surrogates, puts those into that DI water as it's transferring them from the syringe to the vial, and then we purge in that vial with our 3-stage needle. So the lowest port on the needle, purge gas exits, bubbles through the water column, it's collected at the highest port on the needle, and taken to the analytical trap. And then finally, our sample can be stirred during this process using our magnetic stir and a stir bar that's added at the time of collection. Okay, so some of the things considered during our sample collection and prep is the mass of sample that we need to collect, the volume of water we're going to add, making sure we put a stir bar in, and then making sure that that remains leak tight. So having a PTFE septum on our cap, making sure that our caps are secure, tightened, taped for transport, make sure that they remain nice and tight and secure. Okay, for mixing, the type of mixing and the amount of mixing that we would use during purge is going to depend on our soil matrix. So for fine soils such as clays, we need to mix longer, so maybe we need to do a pre-mix before starting purge. And then maybe we need to increase our purge time to make sure that we get adequate contact time between that very, very fine particulate clay and the water so that we can remove more of those volatiles from the clays to the water and then purge them out. We'd also recommend a less aggressive mixing, so in this case maybe the agitate setting, so that we don't create a vortex and then cause those clay particles to clump up and ball up and just create larger blobs of clay that aren't getting adequate contact with the water. For larger particles such as sand, we don't need to mix nearly as long. We can get adequate contact with the water column to release the volatiles into the water with shorter mix times, and then therefore we don't need as much purge time, so we can shorten our purge times. We can also use more aggressive mixing in the case of larger particles such as sand, so you can use the medium or maybe the fast setting on the mixer. And then humic soils require longer mixing times in general because of the nature of the soils. They tend to vary much more from one to the next. That organic matter in the soil is going to change how it releases those volatiles to the water. And then again, the mixing speed is going to be dependent on the specific characteristics of the soil. So some humic soils you may be able to stir very quickly. Others may clump up at high speeds and need to be mixed at a slower speed or even just agitated. So looking at some stirring data, we see that during an in-vial purge of a soil, we definitely get better removal with stirring as opposed to not stirring. Sample heating, though, can also help move those volatiles from the soils to the water phase. And so just as with our sparger purge, we can also heat our vials for in-vial purge. We can set that temperature. We can control what that temperature is. So like I mentioned, higher temperatures can help release compounds, but just like with our purge in the sparger, if we heat our temperature too high, we cause more water moisture that then goes onto our trap and can cause issues. And so here's some purge temperature data. We see obviously at higher temperatures, we release more compound of interest from the soil into the water and then from the water into the gas phase. Okay, so here's a shot of the vial handling on the Atomx, and we see that we have our heated chamber here that our needle protrudes into. So we have control of the temperature of this chamber, and therefore we have control of the temperature of the vial and the purge. All of our pathway here for our gas handling during in-vial purge is heated, and it's inert tubing. And then here's our three-stage needle. We can bring our water in through the middle port. Our purge gas comes in through the bottom port, and then our gases are collected through the top port. Okay, and so then we see here that once leaving the vial, it's then taken over to the analytical trap and the condensate trap, where it's then handled just as if it were a liquid sample from the sparger. So here's some results. 200 ppb standards for 8260. We have liquid sample in blue, and then we have our soil in-vial purge in red. We see here that in our clay soils, with adequate mixing time and with the proper agitation, we can get excellent recovery as compared to a liquid purge sample. With sand, we tend to have a little more trouble recovering certain compounds, especially our heavier compounds stick a little more. And then same with humic soils. We tend to have issues getting our heavier compounds loose. So again, longer purge times, maybe a longer pre-mixing phase to help move those compounds from the soil to the water. Okay, so what are our carryover considerations here? On the liquid side of things, we don't really have issues. We're purging in our vial, our samples in our vial. It never comes into contact with our syringe or with any kind of glassware that the next sample is going to go into. However, we do need to rinse our needle because our needle protrudes into the sample matrix. And then we also want to rinse our water pathway to make sure we don't start building up our internal standards and our surrogates that are added. So flush out that manifold, flush out all the associated pathways between samples so we don't get a buildup there. For the gas side of things, it's the same considerations for liquid samples. Make sure that we have adequate bake and make sure that we have adequate temperatures in our desorb and then our bake out so that we remove all of those compounds from our traps. So conclusions for our in-vial purge. It's more difficult to attain good recovery of heavier compounds in our sand and our humic soils as compared to a liquid purge. But we get good recoveries in clay, even if it requires a longer mixing time. And then sample heating can help with that recovery, especially in our sands and our humic soils. But that comes in a trade-off with water issues that we then have to deal with. Okay, finally, I want to touch on methanol extraction in the last 5 minutes or so that I have here. Methanol extraction is a necessary preparation step for our higher concentration soils. So if our anticipated concentration is 200 micrograms per kilogram or higher, then we're going to be using a methanol extraction in this case. There's two ways to do this. The first is to collect the sample the same as a low-level sample, then do the extraction with methanol in the lab, adding your methanol to the water after you've done the extraction, and then following method 50/30 purge and trap guidelines for sample concentration. Or you can add the methanol into the sample at the time of collection, and then when you return to the lab, take an aliquot of that methanol, add it to water, and then follow EPA method 50/30. Okay, so what are the requirements specifically for methanol extraction? Again, we're looking at 5 grams of soil, and we can change that if necessary. 5 mils of water for the actual purge. Again, adjustable if necessary, if we can defend that decision. Here we have more flexibility in our purge temperature. We can go anywhere from 40 to 80 C to help drive some of those heavier compounds off. We still want to add our standards via the auto sampler, and we still need to have sample mixing during that methanol extraction. So whether it be an agitator or shaking it by hand or a stir bar in a mechanical mixer. So looking at our EPA method requirements specifically, once we have that methanol extract, so once we've done that extraction, how much do we add to water? Well, depending on what we expect our concentration range to be, that affects the amount of methanol that we would then add to our 5 mils of water for our purge and then our trapping. Okay, so when doing a typical methanol extraction by hand, the analyst weighs out 5 grams of soil, adds the 5 grams of methanol, or 5 mils, excuse me, of methanol to that soil, adds surrogates and internal standard at that time, mixes, shakes it for 2 minutes, withdraws anywhere from 10 to 100 microliters of extract, depending on what's necessary, adds it to the 5 mils of water, and then begins normal analysis. With the Atomx does almost all of that for you. At the time of collection, the sampler would assure that 5 grams of soil were collected into the vial. The star bar would be added at that time, the sample capped, and then it's never opened. It's never uncapped from that point forward. So there's no concern of loss of volatiles when opening the cap to add the methanol. The Atomx will add the methanol to surrogates internal standards, mixes the sample with the stir bar that was added, withdraws the extract, whatever amount you set it to withdraw from that sample, depending on what you anticipate the concentration being, adds it to 5 mils of water, and then purges it in the sparger, just as any other liquid sample. And the total runtime to do all of this is approximately 26 minutes, which is pretty good. Okay, so what are our conclusions on methanol extraction? Optimization of our purge and trap parameters remains similar to what we see in EPA method 524 and the 50/30. So when we have flexibility with things such as dry purge, desorb time, desorb temperature, and total amount of gas used for desorb, we can play with these parameters to help reduce water, reduce carryover by our bake out, which is more or less open for our cleanup stage. We can do whatever we want in most of these methods. So again, just optimizing it to get the best cleanup that we can while keeping our run as short as possible. Other benefits of using the Atomx is we have no loss of headspace in the sample vial because we never open it. We don't have to worry about the issues of dilution that are mentioned in the 5035 by adding your methanol preservative in the field. And we have precise volume handling because it's driven by a stepper motor with a syringe and it's automated. And with that, we have just a couple minutes left. My apologies for going long, but I will field whatever questions I can in what little time we have. And then for those that I don't have an opportunity to get to, we will get your email address, and I will be sure to follow up with you at a later time. So no questions will go unanswered, I promise.